Hello, hello. Can you hear me? Yeah,
Yes.
good.
Hello,
Yeah,
yes.
yeah.
Okay, wonderful. So let's take a few minutes before we started so everyone can
No.
join us.
Hi.
Hey, Dilshan, how are you doing?
Good. I'm good.
So let's wait a few minutes.
Amilton, sorry, did he ask you for the passcode when you were trying to join? Just
Yes, I
wondering if
asked it, and yeah, that's okay for me. And also ask you for the link for the audience if the people can join us and to
okay.
watch.
Yeah. So people should have the audience link. So that's the
Hmm,
one they have registered with.
Okay.
Just wondering if perhaps anyone is having like a problem with
Yeah,
like a
people are asking me.
password.
Yeah, people are asking me for the link. So I think people there's some people that lost the link, so that's why. Okay.
Okay.
Okay, I got you. Mhm.
Yeah, people are starting to.
Right. So during the presentation, I think it would be great if everyone keep your mic off and also your camera because of the internet connection. Otherwise, everyone can share your screen and start your presentation. So before starting, the order of the presentation would be Lucas, then Jushan, Bruno. Oops, sorry, I have a problem here. I'm back. Can you see me? Can you hear me? Nope.
We can hear you, but can't see you.
Yeah. We can.
Mm, Okay, just a moment. Sorry. All right, so now you can see me in a few seconds, maybe just a moment. Yeah, now you can see me. Sorry about that. So before we started, the order of the presentation would be Lucas, Jushan, Bruno, and Marco. Okay, so everyone has about 20-ish minutes. Then everyone has your own presentation, and then we can start as soon as possible. Chiara, is that okay if we wait for maybe more 2 minutes?
Yeah,
Okay.
absolutely. Yeah, more than welcome to wait.
I know there are a lot of people stuck in the traffic to arrive for this webinar. So the traffic around the world will be really heavy and change from the conference meetings. So that's why people are a little bit late for a webinar online. So let's wait a little bit more. All right. Can we start, Chiara? Ella, is that okay?
Yes, I think so. I don't see any more people joining for now, but otherwise I will I'll admit them as they join.
Okay, that's wonderful. Thank you. Okay, everyone, thank you so much for joining us for this webinar. The title of the webinar is Green Technologies in Critical Minerals Recovery for Energy Transition. My name is Amilton. I'm postdoc associate at MIT, Material Science and Engineering Department here in US. And I welcome all the panelists for this presentation. Dr. Lucas, Dr. Dilshan, both from University of Brescia in Italy, Professor Bruno Ramos from FEI in Brazil, and Professor Marco from University of Minho in Portugal. So thank you so much for joining us for this webinar. We have a lot of talk. So we're going to talk about engineering, the research development, and also the importance of critical minerals and the social aspects of these technologies and extraction as well. So I'd like to thank from Frontiers to host this webinar and invite us for this special topic. And we are receiving a lot of papers and a lot of submissions, and more submissions are more than welcome here for this special topic. So the special topic regarding a lot of different topics about urban mining for critical raw materials production, development and application of greener technology and critical minerals extraction, metallurgical approach, exploration and valorization of low-grade mineral resource, and organic acid applications for extraction, advanced membrane technologies, and CO capture as well. This topic is hosted by me, Dr. Nelson from FUCAP Business School, and also Professor Denis Espinosa from University of São Paulo. I'd like to invite Chiara and Ella to talk more about Frontiers and about the journal.
Thank you very much, Milton. So hello, I'm Ella. I'm the General Manager of Frontiers in Sustainable Resource Management. And yeah, thank you for letting me briefly talk today. And yeah, I'm pleased to also be joined by Chiara, who's our journal's dedicated specialist as well. I just want to take a few minutes to introduce the journal to you, which is the home of the research topic that we'll be hearing about today, and the home of the research. And if you have any questions about the journal or contributing, please don't hesitate to get in contact with us using the email address that's on the screen. We're always happy to discuss. But yeah, so Frontiers in Sustainable Resource Management is a young gold open access journal. We launched in 2022, and we are indexed with the Directory of Open Access. And our title is also led by Professor Brian Pfaff from Towson University in the US. So really the mission for the journal is to kind of bridge that gap between kind of theory, practice, and helping researchers, policymakers, and society transition to kind of sustainable resource models. And within the journal itself, we have 5 sections, including kind of natural resources, which is the section which houses today's collection that we're talking about. And this section really focuses on kind of, sustainable utilization, management, and development of natural resources and their impact on the environment and human society. So we're really excited as a journal to be kind of hosting this collection and welcoming research in these areas that are going to be talked about today, and kind of accompany that. We are excited that we have the flexibility within the journal, not only to publish original research and reviews, but also a variety of article types such as mini reviews, case studies, data reports, which might be relevant for different authors contributing to the collection. We also have a really good peer review time of around 94 days as a young journal, which hopefully will also appeal to researchers who want to get their work out there into the world. And I really appreciate you taking the time to listen to me today, just a little bit about our journal, and I look forward to hearing about all of the presentations following. So I'll hand back to Amilton now to start them off. Thanks.
Thank you so much. This webinar just exists because of you and because of you, Chiara. So thank you so much for accepting this idea and host us. So that is really great. So we're gonna talk about what is the importance of green technologies in critical mineral recovery and energy transition. So let me introduce myself. I'm a chemical engineer by training. So right now I'm postdoc associate at MIT and also professor in two different graduate courses at the University of São Paulo. I've been working sustainable mining, hydrometallurgy, electrochemistry, membrane science, and circular economy, recovering critical minerals from different types of waste, and more recently using electrochemistry, electrochemical separation. So why critical minerals are so important and why mining is so important? First of all, why mining is being used for several centuries, for many years, and for several applications? Because mining supply different key materials for human society, for our modern society. So here we're going to talk about cement production. We can talk about cement production, steel, but also the most important one here for today is critical minerals for energy transition. That materials, that elements, raw materials that are important for the transition from high carbon footprint technology to low carbon or net zero technologies. And those materials are used for battery production, for example, or gadgets or laptops, notebooks, and also electronic vehicles, printed circuit boards for all electronic equipments, LEDs, lamps, screens, solar panels. All of those technologies can exist based on critical minerals. So, for example, earth elements, nickel, cobalt, and magnesium. And all mining process require a large area for exploration and also a large area to store those dams, waste that are produced during the extractive process, during the extraction. However, recent technologies, for example, for earth element exploration, nickel, cobalt, magnesium, gallium, they explore only less than 3% of resources available in the area. So that's why we need a large area to store those dams as well, those waste generated in the mining processing, physical separation, and also chemical process. But why those critical minerals, those minerals are known as critical minerals? Because of the high dependence of technology and critically in a short and medium term. That means in a few words that those minerals can face a short interruption in the supply chain in a short and medium term in the next 5 or 10 years. And also we have several problems to replace those critical minerals for specific applications. So for example, lithium here is really hard to be replaced for batteries in electric vehicles. So it's really difficult to change for different elements or different type of battery. The same for nickel and cobalt, including for batteries and also for steel production. Gallium, earth elements for green energy, green electricity generation, and also for lamps with low environment and low energy consumption. Also, those technologies, those critical minerals are produced for a few countries in the world. So there's a domain, a market control for a few countries. So for example, lithium production here is controlled by 3 or 4 different countries. So for lithium from brine, we are talking about from production from South America. And also from spodumene, Brazil, Australia, and China for better market. Nickel, 62% of nickel is produced in Indonesia, New Caledonia, Philippines, and cobalt, almost 70% of cobalt production comes from Congo, and also almost 100% of cobalt for battery market is produced in China or by Chinese companies. The same for earth elements. So that's why those minerals are considered critical, because of those markets in global south and in a few countries in global north, mostly in global south, South America, Asia, and Africa. And those minerals are really important and critical for such technologies for energy transition. That's what we're going to talk today as well. So we can detail here examples of earth elements production and application for renewable technology, e-mobility, and defense and space as well. So what is the vision today? What is my personal vision? And that's why we're going to talk today. And that's the reason we have here a special talk about that. So mining should change the mindset from exploring and extracting less than 3% of mineral resource for a more sustainable mining, which by my definition, is a set of mining process and activities related to the production of raw materials from primary and secondary sources near to waste generation. That means exploring resource, both primary from mining and secondary. That means also mining waste, industrial waste, and also urban waste, or electronic equipments, or batteries, or cell phones, solar panels, also, in order to achieve a circular economy and other sustainable approach near to zero waste generation. That means recovering maximum the materials and reducing the waste generation in the process. That is connected to urban mining definition. But sustainable mining definition is more broad. So here we're talking about primary and secondary production resources, and urban mining is more focused on waste generated in the cities, in the urban based on urban activities. So that's the vision and how important urban mining and sustainable mining are for the society to having critical minerals and supplies. So today we're going to talk more specifically about batteries, lithium-ion batteries, as one example of promoting circular economy. So the next speaker is Dr. Lucas. I will let him to introduce himself. We're gonna talk about the importance and the new developments of battery recycling. Then Dr. Dilshan will talk about the environment impact of those technologies, and then Professor Bruno Ramos about the importance of critical minerals for energy transition, and Professor Marco about the social impacts. So that's my brief introduction, a brief overview about what we're going to talk today, and I'd like to invite Dr. Lucas to talk about recycling of lithium-ion batteries. So Lucas, thank you for accepting this invitation. It's all yours.
Well, good morning, everyone. Thanks for the invitation. I'll share my screen and my presentation here with you. Let me know if you can see the screen, please.
Yes, we can see your screen.
Yep. Okay, good. Thank you. So, well, good morning, everyone. So I'm Lucas Guimarães. I am currently a postdoc at the University of Brescia in Italy. And today I'll talk about a little bit about the work I developed during my PhD thesis, which is related to recycling of lithium-ion batteries through hydrometallurgical process. So it is an area that I still study today during my postdoc. And I'll introduce myself briefly here. I have a bachelor degree in chemical engineering from the University of Brasília in Brazil. And I got my PhD degree also in chemical engineering from the University of São Paulo in Brazil. And first, starting with a brief literature review, to know the context worldwide about electric vehicles and these batteries. So nowadays we have an exponential growth of the production of electric vehicles that I'm going to call here EVs. And why does that happen? We have concern, like even higher concern about the, about the environment, about our environment, and what helps to have this exponential growth in the production of electric vehicles. We can say that some policies are being implemented around the world in different governments. In Europe, for instance, is really, really strong this. And so we have policies that are implemented to replace combustion gas vehicles, so combustion gas vehicles fleet, to electric vehicles fleets or hybrid vehicles. So we have several organizations or initiatives that are responsible to implement those policies. And one example is the Electric Vehicles Initiative, or EVI, which was founded in 2010. and is initiative a multi-governmental policy that accelerates the adoption of EVs worldwide. So and how they do this, they helps governments to tackle the challenges related to electric mobility. So this is just one example. We have several other types of organization, even more and more organization, because let's say the objective is to reduce the combustion gas vehicles and substitute them to electric vehicles in order to be an attempt to help our environment. So this initiative is co-led by Canada, China, and United States, and it has over 16 countries participants. And I just brought an image here just to illustrate image from International Energy Agency in 2023, just to illustrate in one decade how this exponential growth, right, of the global production of EVs. So from 2010 to 2022, we can see this huge growth of the production of EVs, and highlighted here is China, Europe, and USA, which are the main places that they have like those strong policies of production of EVs. And how do the EVs operate? They use lithium-ion batteries. So let's say a vehicle that is 100% electric, they use lithium-ion batteries. They work, they function with lithium-ion batteries, LIBs, which Amilton has mentioned. As I mentioned, Amilton mentioned before, we can find these batteries nowadays in devices that we use in our lives every day, like cell phones, notebooks, tablets, laptops, and even electric vehicles. And why those kind of batteries are used today? Because they have longer service life and greater energy stability than batteries used in the past, like nickel metal hydride, nickel cadmium, and lead acid batteries. So as I mentioned before, we have a growth, okay? The production of EVs are growing around the world, and consequently, we will have a growth of LIB's production. And at the end of life of those batteries, we have a growth of residues and solid waste generation. So this image here, this figure here, I just brought to see the behavior, like the same behavior we had on the first image of the global production of EV. Now this is about the batteries. These batteries demand by region, highlighted, of course, again by Europe, China, and United States. And almost in a decade, we can see again the same behavior, this exponential growth, right? So the EV's production growth and LIB's demand will follow. And this is a behavior that will certainly be repeated in the next decades and next years. And inside a vehicle, those batteries, how are they arranged, right? So in the literature, it's common to find a battery called a cell also. So let's say that one battery is equal to one cell. And a group of cells is given a name. A group of cells is a module, and a group of modules is a pack. So in the image here on the right, we can see the arrangement inside a vehicle. Basically is at the bottom of the vehicle, the batteries are arranged, and the number of cells, modules, and packs depends on each electric vehicle brand or model. This can vary depending on the type of battery you use and the brand of the vehicle as well. And it's important to mention that those batteries represent more than 30% of the vehicle's economic value. So they are really important and valuable inside an electric vehicle. That's why the importance of, the importance of them. So talking about like those batteries, like, and they how we can classify them according to the geometry and the format. So we can classify them with 3 different types. So we can have cylindrical batteries, prismatic batteries, and pouch batteries, but all of them have same components, like common components, which are external metal structure, a polymeric separator, current collectors that are made of metallic aluminum and metallic copper, a binder, which is made of a compound named PVDF, a binding glue. This binder is responsible to glue, let's say, the current collectors and the active material of the electrodes. We have the electrolyte as well, which is made of a compound usually of lithium hexafluorophosphate. And of course, we have the two electrodes, one negative, which is the anode, and one positive, that is the cathode. And inside those batteries, it's interesting to say how it works inside a battery. So as I mentioned, like in the positive electrode, we have here the active material of the cathode, which is the most valuable material inside one battery, inside one cell. And it is glued by the binder into this, onto this metallic aluminum current collector. And the same thing for the negative, for the anode, for an active electrode, then we have the anode active material glued onto the metallic copper current collector. And between them, we have this polymeric separator. And it's important to have the separator because you can avoid short circuit inside the battery because the electrodes will be, they avoid the electrodes to be in contact with one another. And how it works during, for instance, during the charge, when we are charging the battery. So during the charge, lithium ions go from the cathode active material to the anode through the electrolyte. So thanks to the electrolyte, this movement is possible of this lithium ion, and that is how the battery works, let's say during the charge and during the discharge. Let's say, for instance, when you're using the battery, the process is the other way around. So we can also classify those batteries according to the composition of the cathode. So let's say a cathode that has a composition of lithium cobalt oxide, we will get the name and the type of LCO, LMO, we have this composition and so on. And the focus of this presentation is NMC, this battery NMC 811, that has this composition, oxide of lithium, nickel, manganese, cobalt, because it was the battery that I focused during my work, during my PhD. So Amilton mentioned already, so just highlight a little bit, that, of course, as you could see inside the composition of the cathode, we have critical raw materials, so critical metals inside, and they are they have high risk of restrictions on world reserves. So the focus of this presentation will be cobalt, lithium, manganese, and nickel, which were the metals that I recovered during my work. So since we have this growth of demand of these batteries, and we have the presence of those critical metals, the interest in recycling of those batteries are growing like higher and higher. And speaking about recycling of those batteries, how are the steps? We can, it's an important step to start with the discharging of the batteries. So we need to discharge the batteries in order to avoid fire or explosions, because if you try to open a battery without discharging it, you can create a fire and an explosion. So it's a dangerous procedure. So it's better to discharge first. Then after totally discharged, we go, the batteries go under pre-treatment, and then we can have the process of the recovery of the metals itself. And the most consolidated recycling routes nowadays are hydrometallurgy, that are characterized by extraction of metals in aqueous media, pyrometallurgy, extraction at high temperatures, so ovens are very used, biohydrometallurgy, that extractions are made by involvement between microorganisms and metals, and direct recycling, which are physical processes without too much chemical alteration. So the objective of my work was to develop a hydrometallurgical route for the recovery of critical metals from LIBs, carrying out characterization, leaching with inorganic acids, and purification techniques. And life cycle assessment was performed during at the end of the recycling road. So it's important as well to mention that the work was in accordance to the Sustainable Development Goals by the United Nations, number 7, 9, 11, and 12. So a methodology about with the flow sheet of the developer recycling route. First of all, starting with a proper discharge of the batteries, then the characterization of them, and then a pre-treatment of the battery that includes milling with knife mills and particle size separations with sieves of different diameter apertures. After we have leaching with sulfuric acid and phosphoric acid, and then purification techniques were tested in studies such as precipitation with ozone, solvent extraction, ion exchange resins. But the precipitation with ozone was the chosen one to follow for the next steps. And in this precipitation, we could remove manganese oxide. The next precipitation was with sodium oxide, in which we could recover aluminum oxide. Then precipitation with oxalic acid, in which we could remove and recover nickel and cobalt oxalates. And then at the end, we had precipitation with calcium hydroxide, in which we could recover lithium hydroxide crystallized. So for the discharging method, I used 20 cylindrical batteries were discharged using nickel, chromium, and copper wires. And these methods to close the circuit and then reaches the voltage to 0 volts. So this method is better than a commonly used method in the literature, that is the use of salt solutions, because using those wires, we avoid to lose material, for instance, for the substance, for the solution, and we avoid as well to change the composition of the battery, the original composition of the battery later on. So it was a better methodology used. And then for the characterization, one battery was cut open with a diamond blade, and then it was manually open, and so the components can be characterized. And the characterization, we used first the crystalline structure analysis via X-ray diffraction, and the active materials suffered this kind of analysis, and the external metallic structure of the batteries as well. Later, we analyzed the surface of the active materials of the batteries with scanning electron microscopy. Then with Fourier transform infrared equipment we used, we analyzed the separators of the batteries. And then the active materials were analyzed chemically with X-ray fluorescence, atomic absorption, flame photometry, and ICP OES. The pretreatment, as I said, were millings. Using milling, we performed millings. We're using knife mills and particle size separations using different sieves. And at the end, Jones rifle splitter was responsible to homogenize and quarterize samples, the final samples that were again characterized. And those samples were used in the next step, which was leaching, acid leaching with sulfuric acid and phosphoric acid. And the parameters studied were solid liquid ratio, acid concentration, temperature, and time of the reaction. For the purification techniques, first starting with precipitation with ozone, in which the objective was to precipitate manganese. I injected ozone into the synthetic solution, which presented the same composition as the original solution with the best condition of leaching in the previous step. And the parameters studied were initial pH of the solution, oxygen flow rates, and time reaction. This is just an example, this image of the apparatus used, in which ozone is generated from an oxygen cylinder. And then this ozone is injected in the reactor where the synthetic solution is. And then the reaction occurs. And then any excess of ozone is converted back to oxygen and is disposed back in the environment. So another technique of purification used was solvent extraction. And the objective was to extract aluminum. And two extractants, organic extractants were used for this. They had, and several different parameters were studied. They have commercial names, Cyanex 272 and DIPA. So we tried and studied another technique of purification called ion exchange resins. So we use these resins, these two different resins with commercial names, Dowex and Leotix TP220, in order to try to absorb and extract nickel and cobalt from the solution. They both have this functional group, bis-2-picoylamine, and represented here. And according to literature, is a very good and selective functional group for extraction of nickel and cobalt. That's why it was used. Experiments, batch experiments, and column experiments have been done for this technique, and with different parameters analyzed as well. So studying of more precipitation with different precipitating agents. So to precipitate aluminum with these conditions, we used sodium hydroxide. And in order to precipitate nickel and cobalt, to study the precipitation of nickel and cobalt using oxalic acid as a precipitating agent. This was the methodology. So it was tested 3 different types of masses of acid. So 0.81 and 1.2 times the stoichiometric reaction mass of this acid. And 2 different temperatures were studied, so 25 degrees Celsius and 50 degrees Celsius. For the crystallization of lithium, it was first prepared and studied a precipitation of sulfuric calcium with the precipitating agent of calcium hydroxide. And again, a similar methodology than the previous one. The masses of calcium hydroxide tested were 0.81 and 1.2 the stoichiometric reaction mass, and the temperature studied was 25 degrees Celsius. And after that, the evaporation of the liquid in the liquor was performed in an oven at 100 degrees Celsius for 24 hours. And then it was possible to have the crystallized lithium in the lithium hydroxide form. So at the end, after the recycling route, life cycle assessment, LCA, were performed for the route. And the product system considered for this was this. It is in Portuguese, but I will translate you. So it was considered like mass and energy inputs and outputs for this. So it's really important in a nice life cycle assessment study. Probably Dilshan will explain more about this in this presentation. The steps considered for this study was the pre-treatment, so milling and particle size separation, the acid leaching using sulfuric acid, the precipitation with ozone, the precipitation with sodium hydroxide, the precipitation with oxalic acid, and at last the precipitation with calcium hydroxide. In order to get the results for the LCA, was used a very known, very good software in the market used to that is really well known to use to study LCA, which is CIMA Pro. And the environmental impact categories studied and quantified were global warming potential, mineral resource scarcity, and primary energy demand. The reference calculation basis was considered the production of 1 ton of lithium hydroxide produced at the end of the recycling route. And the initial quantity considered for this production was the use of 270,000, more than 270,000 batteries. Now, talking about results and discussion of the work, after fully and properly discharge the battery with the nickel chromium wires, X-ray diffraction technique told us that in the cathode, in the active material of the cathode of the battery, we could find this crystalline structure, so lithium, nickel, manganese, cobalt oxide, and then for the anode, the active material of the anode, we could find carbon in the form of graphite. And the chemical analysis corroborated the previous results, in which we could find in the active material of the cathode, we could find nickel, manganese, and cobalt, and then therefore we could find that the type of that battery was NMC 811. Once again, the analysis made on scanning electron microscope, we could find in the active material of the cathode, we could find nickel, cobalt, and manganese again, and graphite in the anode. For the separator, the FTIR analysis could find polyethylene for the material of the separator. The pre-treatment after the 2 millings with knife mills and particle size separations resulted in a mass, a black mass, let's say, proper to use for the next step of leaching, a mass of 573 grams. And it's important to highlight here that with this pre-treatment, all the separators, all the plastic and all the external metal structure of the batteries were completely removed, and the great majority of copper and aluminum metallic of the current collectors were also removed, and just a little bit remaining here in the black mass. So the results, in the best condition for sulfuric acid, leaching with sulfuric acid, showed that it was able to recover 100% of nickel, cobalt, and lithium, and 90% of manganese were leached, doing the leaching with these acids. And it's important here to mention that it's common to find in the literature the use and the injection of conventional reducing agents or optimizing agents in order to get more than 90% of leaching. So reducing agents such as H2O2. And it's important to highlight that this work did not need to inject any other conventional optimizing agents, because the presence itself of aluminum and copper metallic ones in the black mass helped to have to get the results already of over 90% of leaching. So after doing as well the leaching with phosphoric acid, the two were compared, and as we can see, the best conditions of them, we can see that in order to get the same leaching efficiency of sulfuric acid, the phosphoric acids needed to have a higher concentration, a bigger concentration. And also I studied of techno-economic analysis, a simplified one, a TEA, was performed in order to know the leaching cost of the leachings using sulfuric acid and phosphoric acid, and the leaching cost for the leachings using sulfuric acid was the lowest. So the best results of leaching with sulfuric acid were the ones considered for the next steps. The synthetic solution that it was created for the next steps, it has the same composition of the liquor, of the leaching liquor in the using the best conditions of sulfuric acid leaching. The results for precipitation with ozone in the best conditions, at the best conditions, we can say that it was possible to recover 99.9% of manganese and the lowest amount of co-precipitation of cobalt, which was 2%. And the precipitation with sodium hydroxide to precipitate aluminum, the best condition, I mean, it was possible to guarantee 100% of aluminum. So all aluminum was precipitated, and the smallest amount of nickel co-precipitated was 2.9%. The precipitation with oxalic acid, in the best conditions, it was possible to recover 99.8% of manganese and cobalt, and only 3.5% of lithium was co-precipitated. The precipitation with calcium hydroxide at the best condition, it was possible to obtain 78.8% of crystallized lithium in the form of lithium hydroxide. So at the end of obtaining the metal of interest, the compounds of the metals of interest, a final mass balance were considered. So we can presume that in a nutshell, 903 grams of batteries studied generated 50 grams of manganese oxide, 421 grams of nickel and cobalt oxalates, and 73.9 grams of lithium hydroxide. The results for the LCA found in CIMAPRO considered the base scenario of a linear scale up from the laboratory scale to a scale in which we could produce 1 ton of lithium hydroxide. So the quantities of found for global warming potential was 1.16 times 10 to 6 kilograms of CO2 equivalent. And mineral resources scarcity, the quantity generated according to CIMAPRO was 523 kilogram of copper equivalent. And the primary energy demand, the results show that the highest, the most used energy was a non-renewable one, fossil, with the value of almost 20, almost 19 terajoules. So it's important to say that more scenarios can be analyzed, is recommended to be analyzed in order to have a more deep and more profound results for life cycle assessment. And in order to compare as well and discuss the environmental impacts generated. So this was just a base scenario. It's important to also compare a best scenario in which, for instance, we can have the lowest quantities of environmental impact, or compare a recycling route with production route of some compound to see if it's really, to really have a deep understanding of life cycle assessment. And 91.8% of the gases emitted along the route were fossil CO2, and the network diagram found on CIMAPRO said that the use of oxalic acid was responsible for 94% of the environmental impact generated by the routes in this base scenario studied. So the conclusions of the work, some final conclusions, the characterization of the batteries was carried out, which determined that they were NMC 811 type batteries, and it was corroborated by the literature. Sulfuric acid leaching did not require any conventional reducing agents to leach all the metals of interest, and its results were considered for the following stages. The optimized ozone precipitation generated around 99.9% of manganese, which proved to be an efficient technique to be for the purpose. The precipitation with sodium hydroxide and oxalic acid managed to precipitate all the aluminum and all the nickel and cobalt respectively, generating co-precipitations less than 4%. The crystallization of lithium, which with the addition of 1.2 times the stoichiometric reaction mass of calcium hydroxide, generated around 79% crystallized lithium hydroxide. Higher values of the mass of the precipitating agent could be tested to see if the efficiency can be increased. The hydrometallurgical route for recycling NMC 811 batteries was developed, and the critical metals, lithium, nickel, manganese, and cobalt were purified and recovered. The LCA indicated that fossil CO2 was the most emitted gas, and the use of oxalic acid was responsible for the biggest environmental impact rate. And the LCA as I mentioned before, can be carried out, consider different scenarios in order to compare and have deep understanding of the process and of the results and deep discussions, and to ascertain how aggressive or not the route studied is to the environment. So this was briefly a little bit what I developed during my PhD. Thank you so much. Thank you again, Frontiers, for the invitation.
Thank you so much, Lucas. Thanks for your presentation. Now I'd like to invite Dr. Dilshan, also from University of Brescia in Italy. So Dilshan, Lucas, you can share your screen, and
Yep.
I'm gonna pass to Dr. Dilshan to make his presentation. Dilshan, all yours.
Okay. Thank you very much, Milton. Okay, let me share my screen first. Okay. 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 Great. So I hope you can see my screen. Yeah, right. I
Yep,
hope you
can see.
Okay, great. Fine.
Yes.
Thanks. Okay. Fine. So, so first of all, my name is Dilshan Premathilake, and I'm okay. Let's say still a PhD student. So I'm going to finish my PhD in this month, and at the end of this month, by the way, like with the final defense. So currently, I work as a grant holder at University of Brescia, Italy. So in my presentation, I'm going to focus on the recovery and reuse of graphite from spent lithium-ion batteries. So my focus is going to be based on graphite, or the anode part of the lithium-ion battery. Great. And then, okay, so if I move to the next slide, okay. Great. So let me take, okay, great. So this is my content. So I'm going to talk about two studies. First one, I'm going to talk about like the graphite recovery mechanisms that I studied during my PhD, and also the life cycle based assessment about the economic assessment and the environmental assessment. And then I'm going to focus on the how I utilize graphite in wastewater treatment as well. So there I'm going to talk about more about the water treatment or the possibilities of using this graphite for water treatment possibilities. Well, if I give you a brief introduction for this presentation, for the whole study, first of all, like why graphite? Why we need to focus on the graphite? The main reason is that the graphite is identified as one of the strategic material, or like critical raw materials to Europe, and also for other countries as well, like for USA and also for Australia. So the thing is now the graphite is going to be the main ingredient in the anode material in the current lithium-ion battery structure. So we know that, as Lucas and Amilton explained previously, like there are going to be like a very high demand for lithium-ion batteries. So more and more graphite is being extracted for this purpose. And the second point is that most of these graphite ores are controlled by large dominant companies from China. So which means like it can be there can be like supply interruptions in short or like near future as well. So this is going to be another problem that we need to address. So due to these reasons, the graphite recovery, or like recycling of graphite from these lithium-ion batteries is needed to be like addressed. But currently it's largely overlooked because of the less economic value of this secondary graphite. There are other problems as well, like the contamination challenges, because the graphite, when we're going to take out from the lithium-ion battery anode, it's mainly contaminated by the electrolyte, maybe like some metals from the cathode material, and also from it's also going to be subjected into deformities because of the continuous charge and discharge cycle. So due to all these reasons, graphite that we can find it at the end of the lifetime of lithium-ion batteries, it's going to be in a very poor quality. So my study in these studies, my study goal was to identify sustainable methodologies to recover this graphite, and also to give a second life for this recovered graphite as well. So if I just move to the methodology that I adapted for graphite recycling, I mainly I opted for like 3 different methods of recycling graphite based on the current methodologies, but I improved or modified these methodologies little bit, let's say, in a more sustainable way. So the cold process, which is going to be mainly depend on the physical recycling, and the wet process is going to be like mainly depend on the hydrometallurgical methods, and the hot process is based on the pyrometallurgical methods. I will explain each of these processes further in my next slide. So here, in this slide, you can see that how I did the optimization of the 3 different methods that I use for the recovery of graphite. So mainly the physical recovery or the cold process, I optimize the grinding period because I use like grinding and sieving based treatment process to recover graphite from this. So here I try to optimize the grinding time and also the sieve sizes for this one. When I optimize the grinding time, I identified that the 2 minutes is going to be the best time for this grinding, because if I'm going to grind it for more than 2 minutes, I'm going to find like lots of copper particles in my fine fraction, which means like the carbon content is going to be like quite low if I'm going to use more grinding time. The same thing happens when I'm going to reduce the time, because at reduced times, I'm going to have less amount of graphite or carbon material in the fine fraction, because it's not going to liberate all the graphite available in the anode active material. In the sieve size also, I try to optimize the sieve size using like a variety of sieve sizes. And then I identified that 0.2 millimeter is going to be the best condition for the extraction of graphite. In the acid leaching or the wet process, I need to explain that over here that I use aqua regia, like the royal solution, to recover this graphite from the anode active material. I know that you may have like lots of questions why aqua regia, because I had the same questions asked from several co-authors as well when I'm doing this research. The main reason is that I try to use different acids. Actually, I try to use sulfuric acid and then hydrochloric acid, and also I try to use nitric acid as well. But all these options are not viable because of the elevated like for an example, if I use sulfuric acid or hydrochloric acid, I have to use elevated temperatures, and also I have to use oxidizing agents, as Lucas already explained in the previous examples. The thing is, if I use these oxidizing agents or like elevated temperatures, my environmental impact is going to be like quite high for this process. But if I use nitric acid, the problem was that it's going to give you a vast amount of nitrogen dioxide, which also going to improve elevate the environmental footprint of the process. But surprisingly, if I'm going to use aqua regia, since it contains like less amount of nitric acid and more amount of hydrochloric acid, the amount of nitrogen dioxide that I'm going to emit is going to be quite lower. So, and also I could do the leaching at room temperature. So this is the main thing, because I'm not going to use elevated temperatures, which is going to reduce my impact drastically. So this is why I have to opt for aqua regia. In the heat recovery or the hot process that I use, I try to use elevated temperatures over here without using any other chemicals. But the problem was the elevated temperatures was that to decompose this PVDF binders, I have to elevate my temperature up to 500 to 600 Celsius degrees, which is not going to be like a good thing, because it's going to elevate my environmental footprint again. So what I did was over here, I tried to use calcium oxide along with this anode active material, because the calcium oxide can react with PVDF binders at much lower temperatures, decomposing all the available PVDF material. So here I could achieve complete liberation of graphite at 250 Celsius degrees, which is going to be like a great achievement by reducing like comparable amount of heat that I'm going to use for this process. And then I moved to the characterization of these 3 different materials that I recovered from anode active materials. You can see that in the CG and the HG, which means like they stand for the cold process graphite and the hot process graphite. You can see that many impurities are still available in both of these graphite samples. This is because the methodologies that I use is not good enough to remove all these impurities from the final product of the graphite. But however, in the wet process graphite, where I use aqua regia, you can see that the clean XRD pattern, you can see this is due to non-availability of any impurities in this graphite. But however, when I tried to do this analysis through SEM images, I could see that minor amount of impurities can be seen in the wet graphite, but however, compared to the cold graphite and the hot process graphite, it's going to be like quite low. So, which means like the quality of the graphite is quite better in the wet process derived graphite. And then I tried to do a life cycle assessment, the environmental life cycle assessment first, to understand which process performed the best in like recovering graphite. So here you can see that the coal process derived graphite is going to give us like negative impact. This is due to the large amount of copper that I can recycle along with the graphite. Which means like we can identify this, understand this as like if I'm going to recover like copper from this method, it can reduce the amount of copper that going to recover or like extract through the mine. So this is based on the avoided products. I'm going to have negative impact for the physical process or the coal process. But however, the quality of the graphite is questionable because the thing is the quality of the graphite is going to be quite low in this method. But however, like the hot process and the wet process derived graphite show like really high environmental impact. You can see that under different impact categories, I can see higher impact is given off through these two materials. Like basically, this is for the hot process, this is going to be because of the large amount of heat I used and also the electricity that I use. For the wet process, this is mainly due to the acid regions that I have used for the treatment. And the normalization and weighted impact categories showed me that largely it's going to be like the wet process that's going to give us the highest impact rather than hot process derived graphite and the cold process derived graphite. And then the LCC analysis, like life cycle costing analysis, was also carried out to understand the economical performance of the three methods. So here I could understand that the coal process again going to give us like a negative impact. This is because again, a large amount of graphite and large amount of copper that's going to be recycled through the process. But for the hot process and for the wet process, the economic impact is also going to be very high. This is due to the large amount of chemicals, the electricity and the heat that I'm going to use, which elevates the economical impact of the process as well. And however, like this part of the research is already published in Sustainable Chemistry and Engineering Journal, so where you can refer for more details through this article. And then I will just move to my other part of the research, like where I'm going to explain about the methodology for the spent graphite application. So for this one, I use this waste residue that derived from derived from the Lucas process, like Lucas already explained, like his process, like with details. So I tried to use this waste material that going to derive from his process, like which is rich in graphite. It's going to be like 96% of carbon. So I tried to use this graphite for the wastewater treatment process because the graphite is known to be like a good material for the waste treatment processes. So I didn't use it as it is because the graphite is still contain like some amount of trace elements like manganese, like cobalt, like nickel. So because of this, I have to modify this waste graphite to make graphite oxide and the graphene oxide, because both of them are going to be like materials that going to have a very high absorption capacities, so like really higher than the graphite. So this is the main reason why I converted into graphite oxide and the graphene oxide. To conversion of the graphite oxide, I use Hammer's method. It's a strong oxidization method where I'm going to use sulfuric and potassium permanganate along with deionized water. And then finally, once I created the graphite oxide, I tried to convert some part of the fraction of the graphite oxide into graphene oxide using the sonication method. So basically, like the sonication method going to fragmented this graphite oxide, and some of the active sites that are going to attach to the graphite oxide will be lost from this method. But however, like we'll see how they're going to perform. So like finally, both of these materials are used in the batch absorption process for dye and for metal ion contaminated water. So I use spiked water samples to try out these two materials. And then so here in this slide, I'm going to show you the characterization optimization of my materials. So the thing is, you can see in the first, the graph A and B, you can see like the Raman spectra and the XRD patterns of the two materials that I produce. So the red color one is going to show you the waste graphite that derived from the recycling process of the Lucas. So here you can see that we can identify that the graphene oxide and the graphite oxide is largely changed from its current status of the waste graphite. This is because the oxidization going to give you like lots of delocalized carbon atoms. So this is why the D peak, which is going to be the first peak, is going to be quite high than the waste graphite over there. And also in the XRD patterns also, you can see that the graphite peak, where it's supposed to be in 25 degrees, it's already shifted towards 10 to 11 degrees. This is because this is identical quality of graphite oxide and the graphene oxide. And you can see that here, in the SEM images, you can see that the graphite oxide going to contain like lots of, let's say, whitish color, like the very light color. This is because of the high amount of active sites that attach to this graphite structure, which is going to be very helpful in absorbing like many pollutants from the wastewater. The graphene oxide, on the other hand, going to contain like a little bit of active sites, because most of the active sites are going to be like detached from the graphite structure when the sonication take place. But also you can see that the parts are going to be fragmented, which means like the surface area of this material is going to be really high, which can trap lots of pollutants. So here, I try to optimize the absorption of dye and also absorption of metal ions to these two different adsorption materials that I produce from the base graphite that derived from lithium-ion batteries. So in the first one, you can see that how they are going to how I did the optimization of the adsorption time and the initial concentration of the dye, and also finally the adsorption dosage that I have to use. So here I could see that like I did the same thing for the metal ions as well. In both the cases, you can see that the adsorption time or the kinetics are very fast. So I could remove somewhere around 90 to 95% of pollutants from the wastewater within 10 minutes time. But however, for the metal ions, this was like somewhere around 24 hours to receive this maximum adsorption limit. And then I tried to use these results for the adsorption kinetics evaluation. So I tried 5 different kinetic models in order to understand like how they're going to give us like more details about the adsorption process. And with high coefficient of correlation, you can see that like both of these metal ion adsorption and dye adsorption follows the pseudo second order adsorption process. So you can see that here it's going to be like really high, the coefficient of correlation. But however, like the other models also provide us lots of information about this adsorption as well, which is also going to be very helpful in defining their adsorption mechanisms. And also, then we tried to evaluate the adsorption isotherms, again, using like 5 different adsorption isotherms, like the famous one like Langmuir and the Freundlich, and then we use Temkin, Halsley, and also like Harkins-Jura adsorption isotherms. So we tried to use all these 5 different isotherms, and we identified that most like both of the dye adsorption and also the metal absorption, they follow like the Freundlich isotherm in absorbing this material for their structure. So mainly, so this tells us that like this material is going to find in this material we have like surface active heterogeneous surface active groups, and also like the affinity of them affinity of these dye pollutants and the metal pollutants are going to be like completely different from each other. So this is why they are going to follow the Freundlich isotherm model rather than following like the other model that we're going to evaluate. And then we try to do like FTIR analysis like before and after the adsorption to understand further understand the mechanism of the adsorption. So we can see that the first part is going to be the graphene oxide. Before the adsorption, we can see that most of these like the surface active sites like carboxylic group and the hydroxyl group are going to be visible. And then we can see that after the adsorption of dye and after the adsorption of metal ions, we can see that the transmittance in these segments are going to be quite low. This is due to the adsorption of this material in these surface active groups. But however, we can see that the metal adsorption is going to be quite lower than the dye adsorption. So same pattern we can see over here. Like for the dye adsorption, it's the transmittance is really low, but however, for the metal adsorption, it's going to be like quite lower than that. And then with this identification, with this understanding, we try to forecast the mechanism, the adsorption mechanism of these two materials. We can see that figure A going to show you about the graphene oxide, how it's going to behave with the different metal ions and dye adsorptions. We can see that different adsorption, different bondings are going to be present over there, like covalent bonding, the hydrogen bonding, and the coordination bonding, the pi bonding, and we can see like different like bondings can be like produced like from like between these metal ions and the surface active groups. But however, you can see that in the graphite oxide, these bondings are going to be quite larger. This is due to the availability of high amount of surface active groups in the graphite oxide rather than in the graphene oxide. But if you see the cross section of this one in figure C and D, you can see that in the figure C, the graphene oxide layers are fragmented, so there are going to be more cavities inside. So more active, like more pollutants can penetrate into this and then get trapped inside this cavity. So this is why graphene oxide adsorption is going to be quite high in each of the cases rather than graphite oxide. But like on the other hand, the graphite oxide going to be only attached to these surface active groups where it's presenting in the surface and also at the end of each of the layers. So I think like graphene oxide is going to be like better in many aspects rather than graphite oxide due to these reasons. It's fast and also like it can contain more amount of pollutants inside. And we already published this part of the research also in Results in Engineering, and you can refer like more details in this article about like all the other details that I didn't mention because I tried to compress like everything in 20 minutes. So it's kind of hard to explain like everything with details. And if I move to the conclusions, we can identify that the physical recycling is a preferable method in terms of environmental and economic perspectives, but this comes along with low quality graphite, by the way. But if you want to apply this graphite back in high-tech applications like battery anode or energy storage materials, so it's a must to opted for hydrometallurgical recycling of graphite. And also, we understood that during the second experiment, we identified that the high quality adsorption materials can be produced from the waste graphite. It's a good candidate for this purpose. It's mainly this is because of like the elevated or like increased interlayer spacing between the graphite that happened during the continuous charge and discharge cycles. And also the adsorption materials show like heterogeneous structure with different adsorption energies. This is why it followed the Premathilake isotherm model. And finally, the synthesized materials show very high adsorption capabilities, very high adsorption capacities than commercially available graphene oxide and graphite oxide materials. So this is going to be like one of the greatest findings that we ever did during this experiment. So finally, I'd like to thank Amilton and also the Frontiers team for inviting me for this webinar and all of you for your attention. Thank you very much.
Thanks, Dilshan, for your presentation. Just two main messages before we move to Professor Bruno. The first one, everyone is free to open your chat and write questions for everyone or Kino. So then after the presentations, we can open the discussions and answer those questions. And also for this webinar, we divided in 3 different aspects. So the first one, you heard Dr. Lucas and Dr. Dilshan about some examples how we can transform recycling and use recycling to recover minerals, critical minerals for the process and obtain critical minerals. And now we're gonna hear from Professor Bruno how to use those critical minerals for energy transition, and finally Professor Marco for the social aspect and health aspect as well. So, Professor Bruno, thank you so much for accepting this invitation. The floor is yours. So, use your time wisely. So, thank you so much for your presence here.
Well, thank you. Thank you, Amilton, for the invitation. Thank you, Chiara and Ella, for having this ready. And I think it's a very nice initiative, as I mentioned to Amilton before. We know it's very rare to see some journal publicators, like publishers, getting involved into the publishing process, like as in gathering and making some advertisement of science and of the special issue. So kudos for you guys. So let me share my screen with you. I first need to stop here. And okay, you guys seeing my screen? I guess it, right?
Yes, we do.
Okay, so, well, once again, thank you all for inviting me. I'm going to talk a little bit of the challenge that we have in terms of sustainable energy transition with or without the critical minerals. I think Amilton, Lucas, and Dilshan just set the floor very well and showed the importance that these minerals have in our future life, right? And I'd like to start as Amilton first suggested, to introducing myself. So my name is Bruno. I am also, as Amilton, a trained chemist. I have a BSc in industrial chemistry. I've got a PhD in chemical engineering in the field of microfluidics and photocatalysis in Japan. I'm currently assistant professor at Fei University, as Amilton just introduced me before. And I'm also a research associate in the University of Sao Paulo in the Department of Materials and Metallurgical Engineering. I'm heading the Microfluidics and Photoelectric Catalytic Engineering Lab, which kind of tells what is my research focus. And well, in summary, my research could be summarized as written in this slide. So developing and optimizing photochemical and electrochemical processes and equipment. I'm also hosting a guest edition of Frontiers Journal, so Frontiers in Chemical Engineering. So everyone else that won't publish here for some reason can go ahead and talk to me, and we can discuss what we can do in our joint issue as well. So my agenda today is very short. It's going to be 6 topics. I'm going to first talk about a little bit of background, but Amilton and the guys already give a good introduction. I'm going to talk a little bit of challenges that go beyond recycling and how we are looking from it from a chemical and materials engineering perspective. How can we develop other materials that could minimize our reliance on critical minerals? And I'm going to do that in 3 fields, especially that I think are the most important: photovoltaics, electric drivetrains and batteries, and on the hydrogen chain. And then I'm going to close up with a conclusion. So first of all, the background in terms of challenges of what does it mean to transit sustainably between different energy matrices. So this recent review last year just summarized a little bit of the key aspects that are sort of challenging our energy transition. They always do challenge. We have several energy transitions in the past. We've got from biomass to coal, and then coal to oil, and now we're transitioning from oil to sustainable energy systems or renewables energy systems. And they always come with some special considerations that have to be made. So first of all, we have these 5 dimensions that we can group them on. So we got social and political dynamics, and among them, I would like to cite, let me just take the laser pointer here, geopolitics. Geopolitics play a very important role, as we are seeing nowadays, and as we have been seeing in recent years with the critical minerals, especially the rare earth elements. We've got also some energy and environmental sustainability issues, and this comes in terms of, especially in terms of land use. When we think about renewables, there's a lot of issues concerning where to position wind turbines and solar panels because they take a lot of space. We've got the issue of pollution that my colleagues just very brilliantly talked about here before. We've got to consider infrastructure, and this is very key, especially when we talk about transitioning from a liquid fuel to an electricity fuel. As we can talk like that for mobility, right? And of course, governance policy frameworks, they are very important to give us the guideline, not us, but the company especially, to give the guidelines of where they should move to. And we cannot forget one of the key, if not the most important key driver, which is economy and market. So we have talked about types of investment and types of subsidies. So what we would like to focus here today are in these two boxes here. So research consumption, and on infrastructure saying in a larger dimension. So when we talk about the critical minerals in energy technologies, we can think about 4 specific issues that I would like to talk about today. There are many different, but one of them is the photovoltaics and solar panels, EVs and batteries. And when we talk about electric vehicles, I put here the icon of a car, but we can also think about trains, ships, planes, and so on, right? We're talking about green hydrogen and fuel cells, and also on fertilizer, because most of our fertilizer industry or food chain relies a lot on conventional chemical processes that have to be phased out if we transition from oil to different sources of energy. So in terms of photovoltaics, the key elements are listed here. We're talking about silicon. Silicon, albeit, is one of the most ubiquitous elements in the Earth's crust. We're talking about high purity, high crystallinity silicon, which is not easily found, and it's very expensive to process. Silver, indium, gallium, tellurium, and cadmium are commonly involved in solar panels and all in other peripherals of the solar panels. EVs and batteries, we got a beautiful talk by Lucas here before. Lithium, cobalt, nickel, manganese, copper, and graphite are very much in current use. When we talk about hydrogen, and we want to focus, of course, on green hydrogen, which is mostly produced by electrolysis. And then we're talking about platinum, palladium, and iridium, which are quite rare to find and expensive, as you all guys might know, which make it very expensive to transition between conventionally steam methane reform to produce hydrogen into electrolysis. So this is one of the key aspects. If we can get these guys cheaper, we can facilitate the transition to green hydrogen and other green subsidies. And green fertilizers, the ammonia chain, we normally use a lot of ruthenium, molybdenum, and also currently rhenium, which is actually even more rare than iridium. So we got a problem. Well, Amilton showed this picture before. So when we talk about critical minerals, we have to talk about supply and cost. So this is from the perspective of the US, United States. And of course, even though some of these minerals, as I mentioned, they are widely available, they are not maybe widely available everywhere. So they might be available, and they most likely are available in some places where we cannot easily reach, or with maybe are governed by some structures which we do not have always some very easy or predictable relationship. So they are listed as critical elements here. And most of those that we talked about are here in this list, like lithium, nickel, cobalt, graphite, gallium, platinum. They all in the red list, which is a problem. So when we look at the abundance here, this is where I'm the chart that I'd like to show to my students to sort of put things into context. Like I said before, silicon is right here in the rock forming elements. Is one of the most widely available, but because it's very reactive, as you guys know, it always comes combined with a lot of stuff and get it separated and then crystallize into high purity, high crystallinity silicon. It's expensive and wastes a lot of resources, especially water and energy. On the other hand, we have the rare minerals down here, as I mentioned before, ruthenium, palladium, rhodium. They are here, and we would like to move from this place up into here, or at least to use these guys in red, which are the major industrial metals, which can be, I mean, they already have their own mining and processing industry quite well developed over the last century. So it would be a good thing if we can make this move. This shows some of the key elements of the critical elements and where they are used. So here we have, for example, in batteries, we have lithium, the majority, about 70, more than 75%. of the end use of lithium is in batteries. Nickel is mostly used in stainless steel. For photovoltaics, have a lot of tellurium being used in photovoltaic panels as well. And this gives a little bit of a perspective of where these things are used and where, as chemical engineers, which is my field, we can look at of a possible industry where we can tackle and develop new materials that maybe make us rely less on these critical minerals. So the key message would be simply get more baskets. We have a saying in English which says that, like, don't put all your eggs in one basket, right? And that applies also for industrial processes, and I think for catalysts and for other processes as well. So we should do the most we can to diversify our possible raw materials. So for example, here in Brazil, as you guys might know, we have, since I think the mid-70s and the 80s, we have a very strong push towards bioethanol as a liquid fuel for transportation. And this proved to be very intelligent and responsible decision by the governments in the past, because nowadays, even if we have a big fluctuation in oil prices, we still have a very solid and kind of lower cost fuels available, which is ethanol. So this is what our government did. So it diversified its fuel sources from gasoline and diesel, also including bioethanol. And this is also should be done for other processes as well. So this chart here shows the production and the perspective of production for copper, lithium, and cobalt, while the red line shows the primary demand. So we can see the demand is already increasing beyond the production of these three critical minerals, copper, lithium, and cobalt. So recycling alone cannot solve the problem, of course, we all know that. But in addition to recycle and increase extraction and make the extraction, of course, more and more optimized so we can get more of these minerals generating less waste, we also need to address the issue, which is the demand. And we can only reduce the demand if we want to keep growing as a society in technology, if we can diversify our mineral sources, or at least the type of mineral that we have to use. So I would like to start talking about photovoltaics and how can we, or what has been done to move ahead from silicon into diversify to other minerals or other elements that can use. So three technologies that have been growing in recent years are the perovskite solar cells, the organic photovoltaic cells, and the dye-sensitized solar cells. So these three technologies have been growing in recent years. And just to summarize a little bit of them, I'm just going to talk about perovskites and the organic panels, which are the most promising ones. So the perovskites are this type of mineral. They come from calcium titanite. And they have this shape here, the whole ABX3 structure, where A is the cation, and B is a metal in the center. And we have X, which are the halides here, shown in this picture. So the most common materials used in photovoltaics, they actually use organic cations, mostly methylammonium or formamidium, which is quite good because we're using carbon and nitrogen, which is very widely available for us. But they can also use inorganic cations such as cesium. And the metal side, we have lead or tin. So lead, we are starting to try and phasing out lead use because of the waste pollution that you guys are probably aware of lead, and replace with tin, but we still have issues of robustness of the material, yes. So we still have a lot of research to do to improve the robustness and the reliability of tin perovskites. And as the X side, we normally use halides, so iodide, bromide, or chloride, which are also gladly very widely available on us. But in addition to the absorber, which is the perovskite, we also have a different layer. So this picture in the bottom, we show here the typical structure of a photovoltaic cell. So the perovskite, which is responsible for absorbing light and promoting the photoelectric effect, this is the absorber, but we also need a whole extraction layer, an electron extraction layer, and a transparent layer, which is made often by glass, and ITO. ITO is indium tin oxide layer, which is sort of transparent semiconductor, which we can use to make the electric contacts. And the whole extraction layer, we typically use organic materials, but we also can use some inorganic materials like copper, thiocyanide. And electrons in the electron extraction, we normally use metal oxides like titanium dioxide, tin dioxide, or zinc oxide, which are also very good semiconductors and very well established with a good supply chain. So it's quite promising. Again, looking at this table, we can see that titanium is right here in the rock forming elements, and all of them are very abundant in major industrial chemicals, industrial metals. So we can at least guarantee the supply side. So in terms of organic photovoltaics, what changes here is that the absorbent layer is actually composed by two, the donor and acceptor layer. And we normally use organic semiconductors like P3HT, this guy shown here, and acceptor molecules, which are normally based on fullerene. Fullerene, if you guys are like us Brazilians who like soccer, is like the soccer ball carbon molecule with 660 or more. So we have these fullerenes here. They have a very well-distributed electron field, which makes them a very good semiconductors. So we combine these two guys here, and then we just have to add the anode and the cathode. And of course, as with the former solar cells, we need to have a transparent electrode, which is often supplied by ITO, indium tin oxide. So again, all elements here are rock-forming elements or very major industrial metals, which makes it a very promising alternative to high crystalline silicon. So this huge panel, which I'm not sure you guys all can see, not even if I don't know if I can see, it shows the NRL compilation of the best research cell efficiency chart. And what we'd like to focus on is on the blue square here, which is the most common crystalline silicon cells without concentrated, just a flat cell. And it's this line here, right? So if we go on to the end, the most recent high efficiency, best efficiency was achieved was in 26.1% of the theoretical efficiency, which means like how much electrons, how much energy could be generated in the material would be 100%, right? But then because of losses, we have a reduction on the efficiency, and the maximum here would be, that was actually reported, was 26.1. And if we look at the three that I just mentioned to you before, we got the dye-sensitized cells, 13%. The perovskite cells, what I just mentioned to you 2 slides before, is 26.7, and the organic cells are already reaching 19.2. So the perovskite cells already have higher efficiency reported, experimentally achieved, right? Higher than the single crystal silicon cells. But of course, that's not everything, right? We don't only look at efficiency. So we have this golden triangle of solar cell performance. We have efficiency as one axis up here, but we also have the cost and the lifetime. And here, if we compare the perovskite cells, the PVSK, with silicon cells, here's a bit outdated, the efficiency, right? But the cost is much cheaper because, again, it uses more widely available materials, so it's expected. However, if we look at the lifetime, we still have a problem with ensuring the robustness. So while silicon panels last for 25 years, perovskite cells have still a quite limited lifetime that should be improved through research. And I think Lucas just talked about a little bit of the life cycle analysis, and certainly like the lifetime plays a major role in that, right? I mean, if I can use something for 25 years versus using something for 1 year and have to throw it away, then of course I'm going to be the environmental impact will probably be much higher in this case than if I just use the common silicon cell. So moving on to another source of problems, which are the electric powertrains for vehicles and batteries. So can we see a future without lithium? That's difficult, right? So in terms of battery chemistries, the things that are being looked on to replace lithium-ion, but still are just lagging behind. The highest or the most notable contender is definitely the sodium-ion battery. We just saw, I think, 2024, last year, right? Some car makers in China already announcing that they would be making, I think it was BYD, if I'm not mistaken, they will be commercializing cars already with sodium-ion batteries. But, you know, the whole industry still looks at it with some sort of lack of trust. You know, we have to see how it goes before. We also have solid-state batteries, which most often contain lithium. So it's not necessarily a replacement, but still it's more of a gradual transformation to a more efficient way. And the organic radical batteries, which are batteries that are mostly relying on organic electronics. So this compilation by the Fraunhofer, published last year, or 2023 actually, shows the state-of-the-art by then on the alternative to lithium batteries. So if I see here the lithium-ion batteries, they have an energy content with about 200 to 300 watt-hour per kilogram. And this is the key thing that we are looking at. So the mass efficiency, the weight, the energy content per weight, the energy content per volume, and the price per energy, right? I've been recently to Germany where we talked about electric hydrogen trains and electric trains, and they were talking about how difficult it is to install batteries on trains to run on purely on electricity for long distances, especially because of the volume occupied by the batteries. And of course, and the weight comes in, but the volume is one of the key aspects. So looking at volume, weight, and price makes us have a nice comparison. So in 10 years to 2035, they predict that the lithium technology will evolve a little bit more, allowing us to increase almost by 10% or 20% the energy hosted per weight, so going up to almost 400 watt-hour per kilogram, and the price going down from 975 to 45 to 90 euros per kilowatt hour. So I don't know exactly how they assume the lithium is going to become cheaper, but that's the assumption at the moment. If we look at sodium-ion batteries, the green one here, we have a much lower, about half of the energy content per weight, and of course per volume as well, but also we have a cheaper technology, which is predicted to become even cheaper, going below 40 euros per kilowatt hour, and with a slight increase in efficiency to 200 or up to 200, I guess, watt-hour per kilogram, still below what the current technology is, the lithium battery technology is. So three other interesting contenders. These guys, they rely on magnesium, zinc, and aluminum ion batteries. But as you can see from the numbers here, they're still way below the lithium battery. So I guess it's going to take a long time for us to think about replacing the lithium ion batteries. If we consider not only the price, of course, but also the energy contents. The most interesting of this, according to the guys in Fraunhofer, is the magnesium. They said that it has a very strong indication that it can actually double down the energy efficiency, but we're going to see about it. So this chart shows a bit on the production 2022 and the reserve that they had worldwide in the first two columns, and in Europe, especially in the last two columns of all these minerals. So lithium, for example, here, the mine production 2022 was about 130 kilotons, and the reserves are predicted to be 26 kilotons. And in Europe, especially, you can see that this number goes way down. So again, 0.6 kiloton production, and the reserves are predicted to be 0.06, so it's quite small. So for Europe, it would be very strategic to move away from lithium. If we compare with sodium, for example, the reserves are much larger, and the mining already, the current mining production is already quite high, and it's just they don't know how much they are. Just put large here because it's a very big amount of reserve. Same thing goes for magnesium. Zinc is a bit more limited, but still quite a lot, and aluminum is also there's plenty of aluminum around, especially not so much in Europe, but around the whole world. So transitioning from lithium to these guys can be very strategic in terms of the availability otherwise. So in terms of powertrains, electric cars, they use a lot of rare earth elements, as you guys know, especially in the electric motor and the generator. So we have special neodymium, dysprosium, praseodymium, and terbium, which are very critical. We also use some of these guys in diesel cars, for example, or in other cars when we're talking about the catalytic converter or for fuel additives, especially for diesel. But the key consumers, the key places where we use these guys are definitely in the drivers and the motors. And IDTech's recently published an analysis up here. What can be done to replace this minerals? So the key point about this minerals is the magnetic properties, right? And if we look here, this is the typical material used and the powertrains, this neodymium iron boron. So it has a very high maximum energy product, remanence and coercivity, which relates to how much time they remain magnetic after turning off the magnetization and the resistance to be remagnetized again. So the higher this number is, the better. And we can see that none of the other less rare earth alternatives like ferrite and alnico, they can offer some good replacement except for the remnants. But if we look, for example, at the maximum energy product, they're still quite below. The only strong contender also contains a rare earth element, which is samarium, and we also have cobalt, which is also a critical mineral. So the work here is still ongoing, and there's a long road ahead. I think in terms of batteries, we're more advanced into finding other alternatives, but in powertrains, we still have a long way to go. I have to work together with our friends, mechanical engineers, to think about the engine distribution, probably. And this shows two graphs, one for crystal abundance and another one for the commodity cost. So one option, as I mentioned before, was replacing the NFB, the neodymium iron boron, by the samarium cobalt. And if we look here, in the right side here, the samarium is considerably cheaper than neodymium. So in terms of cost, it could be an interesting replacement. But in terms of abundance, it's actually doesn't do much big difference. So yeah, we have to look to the other guys in the periodic table or find other ways to induce magnetism in minerals. So as a chemical engineer, we are also worried about plastics and liquid fuels. And that's where the hydrogen comes in. I think in Europe that you guys are more used, and also in the US. I'm talking about green hydrogen. It's much more of a reality than we have here in Brazil. But basically, green hydrogen is the hydrogen that is obtained replacing the conventional steam methane reform, which is natural gas, by electricity. So the whole idea is shown in this graph here on the right and left side, where we can get electricity by renewable sources like photovoltaic powers or wind power or even tidal power if we have a tidal power available, and then use this electricity to promote the electrolysis of water and generate hydrogen. And when we develop processes in terms of green hydrogen, we have to look at three things: the electricity, the electrolyte, which is the solution where the water molecules are. It can be alkaline, it can be just seawater, which has plenty of salt already, or it can even use a solution using smaller molecules that could sort of aid the process going on. And of course, we have to look at the catalyst. So typically what we have is shown in the right side here. This is a scheme of the electrolyzer. We have the anode, the cathode, intermembrane, which normally is permeable to protons, so we call it PEM, proton electric membrane. And we enter with water in one side, and then in the anode, the water is broken down. We call this electrolysis into hydrogen and oxygen. So we recover reduction on one side, hydrogen pass to the other side, and then they form here as a molecule, and they go out and we collect the hydrogen here, right? And these layers of cathode and anode, they are mostly often covered by catalysts, which can be three types: noble metals, transition metal species, or even metal-free organic materials, but most commonly noble metals. So this paper here, published last year, 2 years ago, 2023, I still have to get used to that. It shows some of the key materials being proposed to be worked on the electrocatalysis to produce hydrogen. And here we have different materials, the classes: alloys, oxides, sulfides, and phosphides, and three parameters: overpotential, Tafel slope, and the resistance. So overpotential means how much additional potential I have to supply to have this current happening, and then basically, which means that the lower this number is, it means it requires less energy to make the electrolysis happen. The Tafel slope is how fast the material can be regenerated. So again, The lowest is number, the best, and this is the resistance. Of course, again, the lowest the number, the best it is, right? Because I don't waste, I don't dissipate electricity as a heat, instead of use it to make the electrochemical reaction. So we see the strongest contenders here are actually these guys that I marked in red. So oxides, we have cobalt, phosphorus, and again cobalt on carbon, and here we have manganese oxide. And the phosphides, which is a combination of vanadium, cobalt, and phosphorus again, and nickel. So, and this is the benchmark standard, which is the platinum. Platinum is the benchmark material used for electrolysis. So we have, for example, for platinum, we have overpotential between 1 and 50. The overpotential depends, again, not only on the material, but also on the structure of the electrochemical cell. That's why it can vary from 1 to 50. The Tafel slope between 20 and 30, and the resistance between 1 to 10 ohms. So we can see that the best guy here definitely would be this phosphides over here. Issues with the phosphides: stability is one of the key issues. And also you can see here a whole list of critical minerals, right? We have vanadium, we have cobalt, and we have nickel. So, we're replacing platinum by these three guys, which are also being in dispute, in competition, I would say, with batteries. So we still have to look further ahead. When we talk about the green hydrogen chain or the green hydrogen economy, we're not talking only about hydrogen. So hydrogen is one of the first things that is produced, but then we use hydrogen in several other processes in the chemical industry. One of them is combination with nitrogen to make ammonia, a combination with preferably sustainably captured carbon dioxide to make methanol, and also to make other fuels, other molecules. We call them e-fuels. And these guys are then, of course, used in other processes and in power generation, in transportation, and for heating. So to make green ammonia and methanol, after, of course, obtaining hydrogen by electrolysis, we have to rely on these catalysts especially. So for methanol, the key FCC, we call the cracking catalyst, is compound of copper. It's comprised of zinc oxide, aluminum oxide, alumina, and copper metal. And to make ammonia, we normally use iron catalyst and also potassium alumina catalyst and also calcium oxide. These are the most common elements. And you see that they're just common elements, common minerals used in industrial processes. So we don't have much a big problem with them. But to make e-fuels, relying especially on the Fischer-Tropsch reaction, we need special elements like rhodium, rhenium, ruthenium, cobalt, iron, and copper, right? So this picture here shows a bit more detail how we can obtain these guys. So from methane all the way down to diesel, we can do it once we get hydrogen by electrolysis. It's a much more green process, but still we rely on conventional chemical processes, which require high temperature, which require high pressures. And to make high temperature and high pressures, we have a lot of emissions involved. So one alternative to avoid that is using modern processes, or as we call it, chemical engineering, novel process windows, which means basically electricity and light replacing heat and pressure. So we talk about photocatalysis and photoelectrocatalysis. Now I'm going to talk a little bit more focusing on ammonia, which is a project I'm currently heading, and our most recent publication in the field. So to make ammonia, we can also, instead of using hydrogen, as I showed before, hydrogen and nitrogen as a combination, we can start from water. So instead of splitting water into hydrogen and oxygen using electricity, we can do that using the same material that's going to make the combination already with nitrogen to make ammonia. So we can do it, we call this solar water splitting or photocatalytic water splitting. Basically, we irradiate material with light. It can be solar energy or UV energy. And then once we make the same conductor separated charges, they can be used electron and a hole to promote redox reactions, and then the water will be broken down and produce protons, H+, which then can combine with nitrogen and the electron on the material to make up ammonia. And there are different ways we can do that. We can do this in a flow reactor like this, in a batch reactor like this. We can do it in a flow reactor using gas, for example, or we can do it having an external bias to help the reaction happen, which is what we call the photoelectrocatalysis. So we published a paper this year, and where we explored 3 materials, very basic materials, which are based on iron oxide, right? We have hematite, which is a conventional iron oxide, magnetite, the magnetic iron oxide, and goethite, which is a sort of iron oxide hydroxide. So these 3 materials, we prepared them in the lab, we synthesized them, and then we use them in this reactor here, which was also designed for this type of process, where we have a specially designed reactor that makes specific turbulence to keep the catalyst inside and more time in contact with the light source, so we can improve the reaction yield. And with that, we could obtain these results that are shown in this box here. So most of the materials used for photocatalysis, I mean, all of them are semiconductors. So almost all of them are semiconductors based on transition metals, like titanium dioxide or iron oxide, which is also a transition metal. And some of them are also including carbon. So what we saw from the literature is that the carbon-based materials, as you can see in the graph on the left, they have the highest specific yield of ammonia, which is a very promising thing. Because again, as I mentioned, we can obtain carbon from biological sources. We can pyrolyze waste. We can pyrolyze textile waste. We can pyrolyze rubber tires, and we can convert that into carbon catalyst. Of course, it takes a lot of processing, but still we can do that. And iron oxide also shows up here as an additive to this material, which makes it a very good candidate. So our materials were quite well positioned within the range of the average yields. So it shows us that we can replace some more expensive materials like platinum, for example, here, by cheaper metals that can be easily prospected, especially in Brazil, where we export iron. So we are a net producer of iron. So, it tails up to our local market as well. This is the paper that we published this year. So if you can check it out, if you feel free. So to summarize it all up, the key takeaways I would like to leave you with is, first of all, the essential role of critical minerals. They are definitely here, and it's going to be very difficult to replace them in the short term. So it's going to take a long time, but still we have to look for alternatives. This should be, and is actually, but should become more and more of an active research line. So recycling is very important, but again, it's not sufficient. So in addition to recycling, we have to invest, as Amilton said before, in sustainable extraction and processing technologies to address the demands that we're going to have. We have very promising alternative approaches, especially in the fields of photovoltaics on the left here, in terms of perovskites. Perovskites are already becoming a reality. They're already starting to be commercialized. They're reaching a very high TRL already. Organic solar cells, still not so much, but they have proven to be more reliable than perovskites and in terms of how long they last. So they have a very strong, promising future. In batteries and EV powertrains, batteries, we already have more of guidelines. So sodium ion is becoming a reality. It's becoming commercialized from this year. So we can look forward to needing less lithium, hopefully. In hydrogen production chain, we need novel catalysts and processes as well. Not only catalysts. If we're talking about energy transition, we should not only think about reusing the same processes that we have, just changing the inlet. So from gray hydrogen to green hydrogen, and then keep everything the same. It's not going to work out. It might work out in the short term, but we still have to look for new processes that definitely reduce reliance on energy-intensive materials and processes. We need definitely a multifaceted strategy. So we have to think about recycling. We have to think about alternative materials, and of course, innovative processing to make the extraction less impactful for the environment. And the path forward is definitely we need to continue optimizing the performance, lowering the costs, and possibly mitigating supply risks, which would involve a great deal of calm politics, which is not very much in our near future. And of course, the future research is definitely involved in scaling up this technology, especially when talking about perovskite and organic solar cells, scaling them up and investing on other alternatives that might give us a better resilience toward climate change and energy transition. So thank you all for the invitation. Thank you, Amilton. Thank you, Chiara. And it's been a pleasure being here today and sharing this with you.
Thank you so much, Bruno. Now, I'd like to invite Professor Marco for his presentation. Thank you so much, Marco, and thanks for still be here during this webinar. Your mic is off.
Yes, I think now.
Yeah.
Now
Okay.
you hear me. Yeah.
Yes.
So thank you, Amilton, for the invitation. So I'm Marco. Thank you for 2 years also for the support, Chiara, Ella. I'm gonna do this really fast because of the time that I have now. I'm the most outlier here. I'm a researcher. I'm a assistant professor here at the University of Minho, but I do a lot of research in health systems. And now I'm starting to look like into the health systems model, how renewable energy technologies, how they can help and how they can fit to the health systems models that we have until now. Just for you to take a look about to the best model that we have of health system performance assessment until nowadays. This is a model that was developed by the European Observatory of Health Systems and Policies. And this model just talk a little bit about like the functions and superficial functions of the health systems that a health system has. And it's a great place to look in how the renewable energies are going to fit into the health systems and where are the places that we can study more and where are the places that we need to look more about it. And for sure, when we look to this model, we need to start to look to the governance dimension, the first one that we have here. Then we need to look to the financing dimension, that's the second one. Then we need to look to the third, to the resource generation dimension, that you have the health workforce, infrastructure, pharmaceutics, etc. And finally, you have the service delivery, that you have here public health, more healthcare, and specialist care on that. And of course, all of these functions and sub-functions to achieve more intermediate objectives and then final goals that every health system has. And the most important, then the 10th one here, the social determinants of health that we have, they are also part and they're also affected by the type of material and energy that we are using in all the structures and all the processes that we have in the health systems. So just to be really fast, when I'm talking about some modifications, process, activities in a health system, of course, that the policy and vision are going to influence that. The stakeholder voice that are on that, the information and intelligence that they have there, and the legislation and regulation that they have. And with this wish, with these policies, with this legislation and regulation, with this information, we can go there and we can try to do something in the health system, but we need to have also money. So we need to have revenue, we need to purchase that, we need to do a lot of things that to have some resources to later deliver this service. So I need to have the health workforce, I need to have the infrastructure, I need to have the pharmaceutical, I need to have all of these resources to deliver public health service, to deliver primary health care service, to deliver specialist care. And for sure, the environment that we are, the socioeconomic determinants of health, is the income and social protection, education, employment, etc. But why I'm talking about all of that in a workshop about renewable materials and renewable energies is to understand how do raw materials and renewable energy technologies are related to health systems. So this is a really good paper that we published just in the end of the last year. And that we are connecting the climate change impacts with the health system components and dimensions that I just showed for you now. And to achieve that, to improve my system, to have better outcomes, I need to have some adaptation in these strategies. So I need to have a more transformative leadership looking more to the climate side. So if I'm looking more to the climate side, I need to look more to the renewable energy technologies. I also need to have a climate smart workforce development. I also need to have integrated climate health information systems. I need to have a more resilient and low carbon technologies, part of the webinar that I have here. And we need to have more adaptive service delivery models. And the outcomes that we want to have, it's to have a more resilient health system, to improve the population health outcomes, and to reduce environmental impact. And this is a really good table that we have. And here you can see that we are the authors, Amilton, Flavio, etc. This paper is under review now. And we have like the future research questions that when we would look to, for example, to mine exposures and health systems and health outcomes, which type of study we would like to see. So first thing that we'd like to see based on our systematic review is the health impact assessment and epidemiological studies. Second one is exposure assessment and biomonitoring, risk assessment and modeling, environmental monitoring and source apartment, remediation and environmental management, and policy and regulatory implications. I'm not going to talk more about it because of the time, but when you look to this agenda and we look to the management side of health systems and renewable energies that we are discussing, we need to look more to the monitoring in the assessment aspect that we have in the health systems. So again, this is the conclusion that of my part of the webinar that I would have, and I have here to show for you. So if I want to have more renewable energy technologies into the health systems, of course, that this needs to be part of the governance. So the leadership needs to want that. Policy and vision needs to be on that. And with that side provided, of course, that I need to have money to adapt and to improve the infrastructure and the resources that they have in the health system. So I need to train the health workforce about that. I need to develop and have more sustainable infrastructure using more renewable energy technology in the health systems. The medical equipments that are being used, with type of materials and energies that they are using. And of course, with that, the services that are being delivered are going to be impacted, like in the public health, primary health care, and the specialist care that usually is the most expensive one. And for sure, when you are looking to the renewable energy technologies and the materials that has been used, of course, that I'm going to talk here about the socioeconomic determinants of health, because usually if you have the economic part, the educational part, the social protection part, the housing part, they are part of the health system because they are the context of the health system. So we also need to look to that side to understand and to improve the health system, to have better intermediate objectives and to have better final goals. And again, sorry for being so fast, but the time that we have just finished. And Amilton, so sorry for being so fast, but I'm here if you need me. And thank you very much for the opportunity. I think we are in like areas really far sometimes, but when you look to the models of health system, for sure that we have these parts here. So thank you very much for the invitation, and I'm open to another invitation and to discuss more.
Okay, thank you so much, Marco. As you said, we are here discussing different aspects of critical minerals extraction and recovery from different sources. So here we had 2 examples for better recycling, then technology for energy transition, and then health system and how those are important in terms of how we should think about in engineering side and technology improvements and taking into account of sustainability and health aspects as well. So to finish this webinar, we are far away from what we planned. I separated here 3 different questions. We receive a lot of questions, and I received message, like my private number here. A lot of questions from the audience. So thank you so much for all of you for presenting, so for being here, making questions, and be part of this event. So I'd like to address to Lucas, Dr. Lucas, two main questions about your process. So you said about your battery recycling. The first step after discharging those batteries is the physical treatment. And the first question we had here from the audience is about the copper content. Did you have any copper in your leach material? I mean, the black mass before for the acid leaching. And you said also the process you developed. I was your co-supervisor, so I know your process as well. You said that you are not using any reducing agent to the process. However, aluminum works as reducing agent. The second question is, how many aluminum you have in your material? Is that enough as reducing agent for the process?
So thanks for the questions. Very good questions, by the way. So the first one about copper, the presence of copper in the black mass. Yes, I had some copper in the black mass. Yes, I mean, the great majority, as I said, could be removed during the pre-treatment, but still like small pieces of metallic copper and metallic aluminum was present in the black mass. And at the best condition of the leaching with sulfuric acid, at the best condition, copper was not leached. Okay, I saw there's a question about it. It was not leached, but at the best condition. But of course, in other conditions, copper was, yes, leached. So which is a relief. I mean, not being leached in this case. And the other one, so the other one is a really interesting question. I must be honest, that was not the focus of my job, of my work in the PhD. But certainly, yes, that probably yes, there is a certain amount of aluminum, a minimum amount of aluminum that, of course, that is able to create this reducing atmosphere and this optimizing atmosphere, and that can, that allow us to have this leaching efficiency like over 90% or even 100%. But since I focus on the general recycling route, that was not the focus, but I found some papers that explain that quite well. So that was the focus, like to analyze and to discuss let's say the reducing effect of aluminum, metallic aluminum, and metallic copper as well in the leaching of those batteries. So yeah, this is something I got really curious to look about and look for.
Thanks, Lucas. There's another question here that I can answer about the presence of cobalt +3 during your ozone precipitation. What happens in the ozone precipitation is you are adding oxidant agent to increase the redox potential, and because of that, cobalt +2 in your solution can be converted into cobalt +3. That's a possibility based on the thermodynamic reactions in the acid solution. I think that's a little bit not possible to have cobalt +3, but it's something that can be studied in the future. However, any chemical analysis we have available in more like possible to make analysis and characterization, it's not available for cobalt +3. It's almost impossible to quantify cobalt +3 in the solution. It's really difficult, I would say, not impossible. So that's why we did not study it. So the final question here from the chat, I'd like to ask to Dilshan. So Dr. Dilshan, thanks so much for your presentation. And this question, we already have this discussion, you and I, in the past. So I'd like to hear more from you. So you said that your approach was focused on the aqua region for acid leaching to purify your graphite and removing metals or any cathode material in the graphite after leaching. So think about like we have Lucas process, then your waste material is graphite. You took this graphite, not particularly this graphite, just an example. You took this graphite and purify into different technologies. So we can use, sorry, it's my dog. So we can use physical material and also acid reaction. So what is the difference between aqua regia and nitric acid in your process?
Yeah, okay, that's a good question. Actually, I had to answer this question like several times during the revisions and during my PhD revisions and everything. But yes, but it's a good question, actually, interesting question. The thing is, like, if I use nitric acid, let's say that I had to use, like, for an example, 100 milliliters of nitric acid for this leaching. But if I use aqua regia, I'm going to use again 100 milliliters of acid, but in that case, the nitric acid fraction is going to be quite low. So this is the main argument, because the thing is, if I use less amount of nitric acid, which means the amount of nitrogen dioxide that it can produce is like lower. So this is the main thing. And also, like, even if we see the life cycle assessment of aqua regia sulfuric acid with electricity plus oxidants, and also if we do the same with nitric acid and with HCl, and also with oxidization agent and all. So we can see that the impacts of aqua regia is quite lower than the rest, because the rest of the processes has to use like H2O2, like hydrogen peroxide, which is also going to give you like lots of impacts in a life cycle perspective, and also electricity. Electricity also going to be like a crucial thing, because just 1 joule of electrical energy going to increase the impact of environmental impact like drastically. So this is the main reason that I have to use aqua regia for the at lower temperatures. But the main problem, as I think, is not this. It's because using of aqua regia can make problems in industrial lines, maybe because of the corrosiveness, because most of the equipments should be like replaced more frequently. This could be like the main problem. But however, since our study was like a laboratory grade one, so we didn't think about this question. We didn't try to answer this question. But however, this needs to be answered like if we're going to scaling up the process. So this is what I have to say about this.
Yeah, thank you so much, Dilshan, for answering your question. I have a particular question to Professor Bruno. So when you're going to talk, so let's finish about that. So we are recovering critical minerals from different sources, from mining, improving mining with more sustainable way, recovering critical minerals from recycling, and supplying those technologies, those materials for energy transition, for example, hydrogen production. If we take into account electric vehicles batteries, for example, we need increase about 40 times lithium production per year to achieve the energy transition. What about green hydrogen or hydrogen technologies? Have you think about that? Do we have any data about that? So I would like to have some comments from you.
Yes, this is a very interesting question. First of all, sorry for extending my time. Just realized how much more I talked than I planned. So, yeah, it's a very important question. Actually, I have a partner here, industrial partner that makes ammonia, and they are actually large, both national, and they are hosted in Norway. And they've been researching green hydrogen for, as they told me, more than 5 years. And they've only managed to install in one plant at a pilot scale because of, first of all, the cost of the electrolyzers, because they become much more expensive because of the minerals. And another sort of unforeseeing damage is that the whole process to make ammonia is tailored for a feed containing dirty hydrogen. So not pure hydrogen, but dirty hydrogen. And electrolyzers are very efficient. They only make pure hydrogen. So the pure hydrogen actually corrodes the tubulation. They corrode the catalyst, so it makes the process less efficient. So they need to change the whole process to make ammonia, right, using the green hydrogen. So it's not just replacing the infrastructure to make hydrogen, but actually it's much more. So imagine that in 5 years, if the leading world company of ammonia, for example, didn't manage to make one single plant in large scale to use green hydrogen, this won't be happening so soon.
That's great. Thanks for all your insights. Thanks for all your presentations. We took so long, but all those discussions, all those topics we discussed today are really great. So I'd like to thank for all of you, Dr. Lucas, Dr. Dilshan, Professor Bruno, and also Professor Marco. But like I said in the beginning, this webinar is not possible without the help of Chiara and Ella and Frontiers for hosting us and trust on us in this presentation. I hope everyone enjoyed. So thanks so much for being here, and I hope we can see together. We can see all of you together soon. So thank you so much.
Thank you.
Bye bye.
Thanks a lot, everyone.
Thank you. Bye-bye.
Bye.